So our first speaker today is Dr. Tom Laue. Tom is the Emeritus Professor of Molecular, Cellular, and Biomedical Sciences and Material Sciences at the University of New Hampshire. His work has focused on instrument and method development for the analytical ultracentrifuge and analytical electrophoresis, and today he will be discussing the energetics of in-solution binding processes.
Well, I want to thank Nanotemper for the opportunity to talk to you about molecular interactions today. And we're going to talk about a very simple framework for understanding all interactions. Some, like drug-protein interactions, you may want to have an interaction occur. You want that interaction to be as strong as possible. Some you don't want to have occur, such as the flocculation of the antibodies you go to high concentration or the increase in viscosity of a solution. All of these depend upon the energy of interaction, and we're going to talk about that process today. First, we're going to start with some fun facts about energy, free energy, enthalpy, and entropy. We're going to describe what those are about. Then we're going to get you into the solution. How far do you have to travel to interact? How long is it going to take? How do you get there? And then we'll talk about the molecular collisions. How frequently do you collide? And we'll touch on a topic called emergent heterogeneity. What happens to the apparent heterogeneity of a solution as you get to high concentrations. We'll talk about the approach of the process, and we'll talk about the desolvation part of the process. And finally, we'll list off some techniques that can get you information about the interactions. So, fun facts about energy. First of all, you're used to talking about the free energy. It's divided into two parts, the enthalpy and the entropy. The free energy is a form of potential energy. It's the maximum work that can be done at temperature and pressure. As an example, a chemical reaction is work. But I want to talk about the generic potential energy. If the potential energy is greater than zero, that indicates repulsion is occurring in the interaction. If the potential energy is less than zero, that indicates attraction is occurring during the interaction. The potential energy is going to be different as we go along a reaction pathway, so that this is going to change. If we look at the overall pathway, that is the final state versus the starting state, we talk about the change in the potential energy, or delta U. And delta U is going to tell us about the probability of a process occurring as well. Let's talk about the two contributors to the free energy, the enthalpy. Enthalpy reflects the electronics and the electrostatics of a process. It includes all the energy of rearranging the covalent bonds, and it includes the changes in the non-covalent interactions that occur during that process. These are going to include charge-charge interactions, charge-dipole, hydrogen bonds, which are a combination of different kinds of electrostatic interactions, as well as orbital contact, the dispersion attractive energies that occur when two electron orbitals contact one another. They usually show up as changes in thermal energy, and we can determine the free energy by looking at the enthalpy, by looking at the change in the equilibrium constant with temperature. And we'll talk about how we use enthalpy, why enthalpy is so important in looking at drug discovery. Entropy has to do with the distribution of energy. So if we have 6 particles and 10 units of energy, there are many ways we can arrange those 6 particles to give us a total of 10 units of energy. So we could have 5 down here, and 1 particle has 5 units of energy. There's 6 ways of arranging the particles to satisfy that. If we arrange them such as shown here, where 4 of the particles have 2 units of energy and 2 have 1, that satisfies that 10 energy. There's 15 ways. There are 60 ways, though, to arrange them, where we have 3 particles that have 1 unit of energy, 2 that have 2, and 1 that has 3 units of energy. If we were to start our system off over here with 6 ways of arranging them, the system would very quickly drift over to have an arrangement that was like this. This is the most probable arrangement. There are 10 times as many ways to arrange the particles like this as there are like that. Entropy depends on numbers of ways. It does not depend at all on the size of whatever's going on. It doesn't matter if you're working with macromolecules or water molecules. When you bind a small molecule into the cleft on a protein, the water that was on the surface of that small molecule and the water that was in that cleft are going to be released. They all gain entropy because there are more ways of distributing the energy in the system. These two will lose entropy, but because there are far more of these, in fact, the entropy is positive, leading to a negative free energy. If you increase the number of particles, that is, if you increase the concentration, as it increases, the entropy increases. Now, in drug discovery, these two are very important. In drug discovery, you're going to be looking for a large negative enthalpy change rather than a large positive entropy change. Why is that? Because if we look at the bound state of the small molecule and binding into the cleft on this protein, there are many specific interactions that are occurring, various electrostatic interactions. There's just the surface of this drug interacting with the surface, the orbitals on the protein. There are charge interactions, dipole interactions, hydrogen bonds. So the enthalpy is telling us about the specific interactions that are holding this molecule onto the protein, whereas the entropy is really telling us more about how much solvent is being displaced as this molecule binds. If I had a hydrophobic pocket on a protein, many hydrophobic molecules would be happy to bind into that hydrophobic pocket. There would be no specificity to that, and so you are looking for a specific binding event for a drug. So you're looking for a large negative enthalpy rather than a large positive entropy. You don't want non-specific binding. One more thing to keep in mind, if you bind a small molecule into a protein, the energy that's holding this small molecule in here now contributes to the overall stability of this molecule. It's going to take you more energy, thermal or chemical, to denature this structure. And it's going to take more energy by exactly the same amount as the energy that's holding that molecule in there. So let's get you into the solution. Once you're into the solution, we have to think about your molecular properties. That is, the number of different native states you have, structures that give rise to whatever functions you have. There can be conformational variants, and there can be chemical variants. These have different lifetimes. Conformational variants, for example, the exposure of a helix, which now exposes a hydrophobic patch on the molecule, that could have lifetimes in the milliseconds. Something like a chemical variant, a deamidation, can have lifetimes of years. Many of the other conformational changes have lifetimes that are on the order of picoseconds and microseconds. The molecular properties refer to the energies that are going to stabilize any one of these structures. They include the interactions that occur within the solid phase and the interactions that occur between the solid and the first layer of liquid around that solid. Those are going to be stabilization energies. The colloidal properties refer to the interactions between the surfaces of these molecules, the adjacent molecules in a solution. And they're going to be controlled by proximity energies. These are through space energetics we'll talk about in just a moment. They also involve the solvent-shell interaction. So when the solvent shell on this molecule interacts with the solvent shell on that molecule, that's going to refer to the colloidal properties. Each of the structures have different lifetimes. It's important to realize that the molecular properties impact the colloidal properties far more than the colloidal properties impact the molecular properties. The exposure of a hydrophobic patch is going to make it far easier for molecules to stick together because of hydrophobic interactions. The charge on this molecule, the colloidal property of the charge, is not going to change the charge on an adjacent molecule. The energy is just not sufficient. We can calculate the distance between you and a nearest neighbor by simply taking the molar concentration, converted it into the number of particles per centimeter. You invert that, take the cube root, and that tells you the distance between the molecules, between the center of these squares. For 10th molar sodium chloride, you're about 2 nanometers apart. If you're a macromolecule, you have to take into account the size of the macromolecule. If you simply subtract the diameter of one of these molecules from the center to center distance, that gives you the edge-to-edge distance. If we look at the distance as a function of concentration, I want you to note that this is a log scale. As you go from 0 to 50 mg per mil, there's a very sharp decrease in the average distance between molecules. It drops from over 100 nanometers to less than 10 nanometers. By the time you get up to about 100 mg per mil, you're on the order of 10 nanometers or so. And you should pay attention more to the edge-to-edge distance for macromolecules. You can talk about the center-to-center distance if you're talking about small molecules. This is for something at 65,000 molecular weight. This is for something that's more like 200,000 molecular weight. As you get to higher concentration, the distance dependence is less steep. You're going to diffuse to your target. The only way you can get there is by diffusion. The diffusion is caused by quantum mechanical fluctuations in the temperature and pressure in the solution, which bumps into the solvent, into the solutes, and makes them move around. You get a constant if you divide the average distance moved squared divided by the time. And this quantity, the diffusion coefficient, is also equal to the average background energy. That's just the gas constant times the temperature, divided by a quantity that contains information about the solvent, the frictional coefficient, which is the viscosity in the frictional coefficient, and the size and shape of the molecule, which is in the Stokes radius. So knowing the Stokes radius is going to be important to understanding the frictional coefficient and how fast a molecule is going to diffuse. In general, the diffusion coefficient is a weak function of the molecular weight. It goes as the cube root. Depends upon the size and shape through the Stokes radius, depends upon the solvent, on the viscosity. If you're talking about the interaction between two molecules, you simply add the diffusion coefficients for those two molecules. So the diffusion coefficient of protein in the drug, you add those two diffusion coefficients together. In general, the molecules are going to move far more by diffusion at short time scales. This is now 10 microseconds right here for a macromolecule size of an antibody. The molecule is moving far more by diffusion than it is by either sedimentation or electrophoresis or column chromatography. It's only when you get out to about 10 seconds that, in fact, the molecule has moved as much by the sedimentation or diffusion or the elution of the chromatography column than it does by diffusion. So short times you diffuse far more than you move by transport. The length of time between collisions is going to depend upon the size of the molecules. The open squares are for 65,000 molecular weight. The closed squares are for 200,000 molecular weight. And you can see, again, this very sharp decrease as you go from 0 to 50 mg per mil, down to about 1 microsecond from 100 microseconds, and then a slower decrease as you get out to higher and higher concentrations. If you turn that around and ask about the number of collisions per second, and again, down here, you're going to go from 10,000 collisions per second at 1 mg per mil, and you're going to end up with 1 million collisions per second, or even 10 million collisions per second, depending upon how big you are, as you get up to 50 mg per mil. So now you're ready to interact. What's going to happen as you diffuse towards your target? Well, we're going to divide this into two parts. The first part is the approach, and this is governed entirely by the colloidal properties. It's going to what's going to happen is going to depend upon what's going on with the average values on your molecule. So X is any property. It could be the charge. It could be the exposure of a hydrophobic patch on your property. If this property, the average value for a small number of molecules over a long time is the same as it is for a large number of molecules over a short time, this is the ergodic hypothesis, then the solution, if these are the same, the solution is homogeneous with respect to that property. If these two averages differ, then it's heterogeneous. That's the basic definition of heterogeneity. And since fluctuations impact this average time, and since the average time between collisions decreases as you go to higher concentrations, you can end up with emergent heterogeneity. That is, the solution appears to be more heterogeneous at high concentrations than at low. The second part of the process is desolvation. That's going to occur from the point where the two surface water molecules around the surface of each protein begin to interact. It's controlled by both the colloidal and the molecular properties. It's going to involve both the removal of water, because remember, the orbitals have to touch in order to have binding. So you have to remove the water that intervenes and any other solvents that are in there, sugars, salts, and so forth. We tend to focus on the first solvent shell. There's good theoretical justification from molecular dynamics and from experimental, from NMR. If you don't desolvate, you're not going to interact. You're not going to bind. So let's look at those two steps. The interaction approach energies can all be described in this way. The potential energy is going to depend on the product of two properties and the distance between the molecules. So, for example, for charge, it's the charge on molecule 1 times the charge on molecule 2 divided by the distance. This n is the distance dependence, and it's 1. If we were to look at the charge dipole interaction, that'd be r squared and so forth as you go down the line here. As these two molecules approach, this potential energy is going to change. And I want to emphasize that this approach that I'm showing here is for a particular orientation between the molecules. So theta indicates that these interactions depend upon the orientation of the molecules. Gamma says that it depends upon the ionic strength of the salt concentration, salt type. The energy profile shown here for this particular approach, you can see the energy goes up, there's net repulsion. This repulsion out here is due to the charge-charge repulsion that can occur. This peak right here is an activation energy. It's going to control the rate of this reaction as this comes up over this hill and down into this valley. And as shown here, this is going to appear to be an irreversible reaction, not because the molecules can't approach one another. The distance from this peak down to here is about 4 times this dashed line, which is RT. This distance is more than 10 times that. And that is going to dictate the probability of an event occurring. So if we look at the probability as a function of the potential energy, the ratio of the potential energy to RT, the background energy, for here we have a distance of about 4 times RT. That's going to correspond to about a 5% probability of the molecules getting past this hill and down to this well. This distance here going in the reverse is over 10 times. There's less than 1 in a million chance of the molecules actually coming apart again. Energies are system properties. They depend upon the salt concentration that's shown here with this exponent of the inverse Debye length, which depends upon temperature and the ionic strength and the distance between the molecules. The takeaway from all this is that as you increase the salt concentration, you're going to have a much greater impact on the charge-charge interaction out here, this tail out here, than you are on these closer range interactions, charge-dipole and dipole-dipole interaction. And then this molecular dynamics modeling shows what happens as you increase the charge on the molecules. You're going to increase the repulsion between them. It's going to require a higher salt concentration before you begin to see aggregation. It also depends upon the dielectric constant. This is something you have some control over when you're doing formulation. For reasons that no one can explain, salt has no impact on the dielectric constant, but small uncharged molecules like ethanol, mannitol, sucrose, these molecules, if you make a 1 molar solution, say, of sucrose, you will decrease the dielectric constant from 80, which would be what it would be just pure water. It would decrease down to about 73 or so, 73, 72, as you went to 1 molar sucrose. You get a much larger impact on the dielectric constant when you add dipole, molecules that have dipole moments, like glycine. And these are going to weaken all those electrostatic interactions. So, for example, arginine, which is widely used in formulations, a 1 molar solution of arginine has a dielectric constant of 140 or more, and that just totally wipes out all the electrostatic interactions. It's going to wipe out the charge-charge interactions, which would make the approach of those two molecules far easier, but it will also wipe out the charge dipole and dipole-dipole interactions, those attractive electrostatic interactions. Now, arginine has impact on protein-protein interactions well beyond its impact on the dielectric constant, but it's important to keep in mind that it's going to impact the dielectric constant and it's going to change those approach energies. Second step is desolvation, and for desolvation, I want to emphasize there's a difference between hydration and solvation, and John Carpenter is going to emphasize this again. Hydration refers to the water molecules around the surface. It's accessible experimentally by a variety of techniques. There's a good set of papers, large set of papers, that indicate that you bind roughly 0.3 grams of water per gram of protein. That corresponds to 1 solvent shell of water around the outside. Now, when we're desolvating, we now are talking about bringing these two molecules together, and we're looking at what happens when these two surfaces get close together, close enough that those first water shells begin to interact. And that's going to occur out here at about 3 angstroms. If we were talking about something like a salt, such as sodium chloride, that would be down in here around 1 angstrom. If you're talking about a sugar molecule, sucrose, something like that, that would be out here at 5 or 6 angstroms. You have to get rid of those molecules. You have to drive them away before those two surfaces can come into contact. Now, if you're trying to prevent molecules from interacting, you want a strong solvent shell. So if you are looking to bind the water tightly to the surface, you would put something like carboxylates, aspartates, and glutamates. It's a very unfavorable process to remove water from the carboxylate anion. Same is true with the ammonium, so lysine side chain in its charged state. Ammonium is also going to hang on to the water quite tightly, but it depends to a great extent on the exposure of the side chain as to how tightly it holds on. Arginine is not a good choice. It doesn't hold on to the water nearly as strongly. And so it is not going to hold on to the water, and there's a greater tendency for molecules to be able to interact if you're trying to make a strong solvent shell with arginine. Now, the hydrophobic surface, water would prefer to be in the bulk. So there are fast kinetics. The water exchanges very rapidly. You can see with the bulk solvent, and if you have a hydrophobic surface, it'll tend to come off. If you have a charged surface, as is shown down here, the water molecules tend to hang on for quite a while. Solvation has an impact on interactions. And again, this emphasizes what I just said before about the pathway of approach is very important as to what you're going to see in terms of these proximity energies. So if we bring these two molecules, these black patches that are on this molecule are hydrophobic surfaces. If they approach from a hydrophilic side, you end up with a profile that looks like this. There's good repulsion up here. The molecules are not going to interact. It's likely there's charges on those surfaces. They're going to hold on to water. So this would tend to be a good situation. The molecules are not going to interact. But if I simply flip these molecules around so that the hydrophobic patches you're approaching with those two hydrophobic patches facing one another, there's going to be a net attraction. And in general, once you get to within about 1 nanometer of your target molecule, so if you're coming up to about 1 nanometer, you're not going to change which faces are going to be interacting. The tumbling time of the molecules is too long, and there's not enough torque with the charged dipole interactions to rotate the molecules. For small molecules, that's not true. You're going to be able to torque the small molecule, and the molecule will tumble much faster. So even as you get very close with a small molecule approaching a macromolecule, you tend to average all the surfaces on the small molecule. Finally, we're going to talk about how we can characterize these interactions using first principle methods. Over here is a list of a variety of techniques that can be used. They're first principle, that is, they go back. You don't use a set of standards and compare your results to standards. The data that you obtain stand on their own. So things like analytical ultracentrifugation, static light scattering, dynamic light scattering, microcalorimetry, chemical denaturation, thermal denaturation, NMR, mass spectroscopy, and analytical electrophoresis all provide you direct insight into the free energy of binding. And for example, if you're binding, again, if you bind a small molecule onto a macromolecule, you're going to increase the temperature needed to denature that molecule. You're going to increase the chemical concentration needed to denature that molecule significantly, and by an amount that's equal to the energy holding that small molecule onto the macromolecule. The strength of interaction in general with all these first principle techniques, the strength of interaction is far easier to obtain than the stoichiometry. That is, how many molecules are actually interacting. And each of these methods has their strengths and their weaknesses. I do want to mention that you cannot measure the charge on a protein. I'm just going to mention it here. There is a technique called analytical electrophoresis, which will allow you to measure it with small quantities of material rapidly and with great accuracy. And you can be way off. You cannot calculate the charge on a protein, so you don't know what that contribution is to the approach energies. So with that, I've been blessed by having many, many people that have had the opportunity to work with over the years, and I thank you for listening to the talk.